USA.
But it's should a lot considering tradition.
He was one from the USA.
No, yeah.
Outside.
He's a problem. But when it's a lot, it's gonna be like.
It's jam.
Jam is generation.
When? I don't know when. It's said that the government of Mexico, they approved this decision.
I have a look.
Okay.
My timetables on me.
Morning.
At least one year.
Yeah. No. I don't think so. US is another stuff. Only half an hour to see the sunlight a week.
Is number one. 40%. That's the 19 minutes. But drug dealer number one. He was named as number one. I'm drug dealer.
He was very like loved in the state. People loved him because he was, for example, if during the time he would come and all the all your shells would be like put in a special container for you to not call the police, but he would pay for everything. You can order everything. He built a building in a university. So the curious thing is that was a chemical engineer, so I think he was recruited.
You mean commercial orders?
Like chemical engineers.
Constructed a building in a university.
But moreover, he said us that you can join to all the sections.
You
Remember there was 10 sections. He said that we can join.
Yeah, waves.
Okay, good morning everyone. We had 2 lectures in 2 weeks ago, right? In the last 2 lectures, we did something about wind and the calculations for wind force on your offshore structures. But today, we will focus on waves, because like I said in last lectures, on your offshore structures, we have 3 main forces: wind, wave, and current. Okay? And today we will focus on waves, and in some estimations we also include the effect of the current. So today the 2 lectures are mainly on the waves, but in next 2 lectures we will do something about the structure motions because of your waves. But anyway, in the very beginning of this lecture, I would like to show you a short video to feel the wave in open sea. But actually it's still very close to the coast. So, and you can see that this scale is huge, because roughly a person should be 1.8 meters tall, roughly. But you can see that the wave height, it's probably about 20 meters or 30 meters in some cases. So you can imagine that if the load is acting on your offshore structures, you can imagine that, of course, in our design we should leave enough safety margin for your structures and for your risk assessment. So in some cases, it's even higher than your structure. Must be a very good experience.
Faster.
Done. It's done. It's a big one. It's not working. Anyway, so from the previous video, we can see that in your design, of course, we need to include the factors from the waves. But just for wave, we actually have many reasons. Probably it's from wind, probably it's from the earthquake somewhere, or of course we know that because we have sun, we have moon, and we have rotation. So it's another big reason for the current and waves in open sea. But if we put them together, as we know in last two lectures, we can use a density map to present the wind or something in a frequency domain, right? Actually, to waves, we can also use the similar method, and we can use a map like this to present the features of the waves or a group of waves. And due to different reasons, they actually have different wave period, or in another way, we say that they have different frequencies. If we put them together, you can have a look and you can have a comparison. For different reasons, they have different periods, like in this map. So, regarding the forces for waves, we know that gravity, of course, is very important to generate waves. Surface tension, because if you have water surface, you have wind, you have friction, right? And that is because of the surface tension on this surface. The other one is probably you haven't heard that before. We call that Coriolis force, and it's from the self-rotation. Anyone else? It's from the self-rotation of our planet. About this effect, I can show you an animation, like here. And you can imagine that if you have a rotation or rotating plate, and we put this black ball in the center, and you hold that. But once you release the black ball will go to the edge because of the centrifugal force, right? But to the red point here, if you just stand on this one, you can see a very strange curve, right? Like if you just make a record, it will be like this. It's an arc. To our planet, imagine that if this black point is a water particle, we also have the same effect in open sea, right? If you have the planet rotation. That's the reason why we can have this good video, and I can show you something about the Coriolis effect and the relationship between this effect and the our weather, right? When you watch TV, you can see some videos in this way, right? The motion of the cloud. But why we always see something like this? We have an eye in the center, but it's like a rotation around. I really need sound. So as you can see from this video, I do the presentation for him. You can see the rotation, and the rotation direction is from west to east. But because we have the planet is a round one, and if your country is big enough, you have two places. This one is close to south, this one is close to north. But you can imagine that the linear speed is different, right? The angular speed is the same. So that's why if you take an airplane from south to north, for example, we stay in north part. So you will see the plane like a curve, because when you take off, you have a greater speed at this point compared to this point, right? But if in south part, it's different, right? You can see a curve in that way. So if you have a group of cloud and the area is really big, we have this effect, right? Here is the north or south, can't remember. But you can imagine that we have a better presentation here. From different sides, they have different velocity, right? It means something will be changed, right? And here, the pressure is low. In other areas, the pressure is high, so they always go to the center. But they will have a small direction. That's why you can see the rotation of that cloud eye. It's finished. So, because of this effect, if we are in north part and we have a low condition area, and in this area the pressure is high, here is pressure low, and we can imagine that the cloud will go to the rotation eye, right? But you may see something like this, or something in that way, right? But I don't tell you now. If I tell you it's in the north part and the planet rotation is from west to north, can can you tell me which direction you can see for this closed group?
Left side.
Which way?
Oh, the right. To west, to north.
So if you go to YouTube and watch the video again, you will find that in north part we will have the anti-clock direction, and in south part you can see it's in clockwise direction. Okay, and this is because of the Coriolis effect. But anyway, we have wind, we have earthquake, we have some other factors, we have waves. Now, if we have only one wave, a single wave, and if you just look at the water surface, we will see something like this, right? And usually, we can present this surface with a function like a sine function or a cosine function in a format like this, right? But actually, we have a more complex form, because when you present the wave height, imagine that when you stand at different place, you can feel different height, right? It means I should have a function. In this function, I should have a variable. It's the location, right? If you stand on just one point, but with the time change, of course, again, you can feel the change of your wave height. It means when you present the height in this function, we should have another variable, right? And from the form, you can see that the basic format should be like this: sine or cosine. So, now I think I can give the equation, and usually we use cosine. In this way, okay? In this expression, you have the location, you have the time, and we have two parameters, k and omega, okay, to control the shape of this water surface. But if you just look at this water surface, we also have some parameters to present the features. The first one is amplitude. Is here to control the maximum height, right? And we have the wave height. If you stand here, you can see the top, and we can measure the height. It will be double of the amplitude, right? And in just one cycle, we have a length. Usually we use lambda to present the wavelength. And of course, if it's about time, we should have a period. We use capital T to present the wave period. Okay? And here is wave height. 1, 2, 3, 4, 5. 4 or 5 parameters. We can define a wave. or we can define our regular wave. And please remember that if we use something to present this, we should include the location and the time, because the height change with location, change with time. So, if we define the regular wave with this format, you can see that the wave will always go forward with the time, right? Because we use a cosine function to present the wave height, and we know that to a triangle function, 2 pi is always very special, right? Because after every 2 pi, you have the same thing. So for k and lambda, we have this definition. In every 2 pi, you have k waves. Here is length, here is the number, and we define that it's in 2 pi. About time, we also have similar things. Here is the wave period, here is the frequency, and we define them in 2 pi. Two important limits. So, if we have the definitions like here, and we can write in this way, right? We can find out the relationship between lambda and period. It's k lambda equals to omega period. Okay? Am I right?
One question.
Wait. Did I miss something? Oh, I need more information for this page. do it next time because I need more details. Can't finish today. Look at this page. Another thing to waves, when we look at a wave, probably in your mind, the wave is just going forward, but actually it's not, because the water particles, the motion is like in a circle, only in a circle. They don't just go forward, okay? And you can look at this animation and feel the particle motions. Okay. So actually, if you don't have current, if you don't have wind, you just put something floating on water surface, they will just stay in that area, right? And they go up and down. You are right. They go up and down, and probably they just have a motion in a very small area, but they don't just go forward. 5 years ago, as you know, we had a big earthquake close to Japan, and they have many ships lost. And after several years, you may find that in Australia or in New Zealand, but it's not because of the waves, it's because of wind and sea current, okay? Because we can define the water particles in this way, I mean the motion, and now you can see that if we have a function including a parameter omega, that's really good because we need angular frequency, right? But from this picture you can see that if we can just go down to sub-C, you can see that the effect of waves will get smaller and smaller and smaller, and to some points it will be zero or very, very small. So in modern ship design, there's always a theory. They hope they can design submarines, because if you go down enough, and roughly we use half of lambda, you will have no effects from waves, no matter how big is it. Another thing is the circles for water particles, they will change. I mean the shape, they will change with the water depth. And if the water depth is big, you can see it's just like a round circle. But if close to seabed or in shallow water, it will be something in this way, and not a round circle anymore. They change with depth. So from this one, you can see that if I put something floating on this area or on this point, it will just go forward and backward, right? They will just stay in that area. And when we define the radius of the water particle motion circle, we can use this way. It's an estimation. And here is the wavelength. So to a regular wave, if you know the amplitude, if you know the wavelength, we use a pi for constant, and if you know the water depth, you can estimate the particles motion circle. Okay, and as in previous page, we always define that if the water depth is 2 pi, lambda, half lambda, R will be minus pi, right? If we do a case study, the amplitude is 3 meters. What is R? We can do a quick estimation.
What's the lambda?
Is that a big value? I can't find my calculation. I think it's about 10 centimeters, or roughly, right? It's something like this, right? Am I right? It's about 0.1 meter, right? This circle. So you can see that the amplitude is 3 meters and the wave height is 6 meters. It's quite high. But when the water depth is 1.5 meters underwater, the particle's motion is quite small. And if you have a submarine with this water depth, you feel nothing, right? Because it's quite small to the scale of your size. So, after you know the expression for a regular wave and you want to estimate pressure on something, we can use this equation, right? We want to know the pressure, and of course you know the pressure from air. And if you have your water depth is HB, previously it should be like this, right? The pressure from air, pressure from water. But now, because we have wave and we have a shape in this way, we need to add something or minus something, right? So we can use the expression of the wave or regular wave, kx0 omega t. Here is for wave height. Because of the wave height, you have another additional pressure. The term is like this, right? P additional. About the energy. Because we have wave height, of course we have potential energy, right? And for potential energy, we need to define the height, and we can do integration from the very beginning to the other end, right? And it's a function of your location and your time. For water, we need to know the density, we know the gravity acceleration, and here is the variable for height, and we do integration for volume, right? And this part is for a very small element, no problem, right? And then, as you can see from my slide, we can take the area element of this part out, SDA, and we still do the integration in this range, and we can write in this way. So now the integration is just for the height, and then after that we can open this term. It will be rho g am I right? Rho g, it products, no problem. So for potential energy, we have an expression like this, and if you stand on the reference plane, it should be 0, right? If you don't have any waves and you have the calm water, it means H is 0, and we can just define the wave energy in this way, right? If you stand on this surface, okay? But please remember that it's just for potential energy. Now in this expression, we don't have any motion. But actually for wave energy, we should have two parts.
That limit of the integration, how do you decide? Minus h2 function of x and t. The integration limit. No,
Here is a function.
yeah.
Here is not a fixed value because
No, but it's we have the reference plane and the wave goes above that.
yeah.
So that's that.
So here is 0. Here is 0 if you stand on the calm water surface, and here is the expression, and you can find that from your wave function. Okay. But actually, I don't think you can define the energy by your handwriting. We always use program. But here is the basic theory. About wave, another thing is, as we know, we can use a very good function to present the wave surface and the wave speed. And if we just look at the wave, it's like the wave is going forward. But actually, on water surface, in most cases, we have many waves, and they stay together and going forward together. For example, we may have two waves, and they travel together. The first wave expression is here. The second expression is here. So if you put them together, we will have a surface like this. And it's like the wave is going forward in this way with this water surface shape. So imagine that if you have a very, very good estimation and a very, very good computer program, you can estimate the wave velocity going forward, right? If your ship is just going forward with the same velocity like the wave group, it's like you always have no waves here, right? So if you can find that point, your ship will be very stable. But in most cases, you can't do that because we have too many waves and it's a combination of more than 100. So theoretically, we can have a combination in this way. We put the expression together, we will have a wave combination or a wave set like this if you just look at the water surface. So it's quite like the real thing we can see from the open sea. But actually we can use the expression in this way to present the water surface. So, in the previous part of this lecture, you know that we can use only one function to present a regular wave, a single wave. But in true case, in most cases, it's like this. So actually, we have two different methods in your design. The first one is we can use a single function to present a regular wave. But in this design, or in this calculation, please remember that we always use the maximum height because you have only one and we need to leave enough safety margin. So the better one is the second one here in the bottom. We assume that the wave is random and we use a combination like this. It's much more reliable for your design, and of course in a real design cases we always use the bottom one. But in terms of the coding, the program coding, we have another two categories. The first one is we can use frequency domain design, and the second one we can use time domain. In most cases, I think, at least according to my experience, we use frequency domain, and we can apply the density curve. Okay, use the density curve to present the feature of that combination here. Okay. When we present a combination of waves, sometimes it's from the observation for open sea area, and we make some records in many years, and we can have a reference book. But just in your observation, we have a very important parameter for waves. It's very straightforward, and we call that the wave height, right? You can just measure the wave height and make records. So, about wave height, we have different definitions, and sometimes you can see RMS, sometimes you can see M or HS. Anyway, usually we use M or S to present a single wave height. So in your record, for example, we have a case here. We do 6 observations. In the first time, it's 50. Sorry, 5.3. Second time it's 6.1. One, two, three, four, five, six. In this case, we have 6 observations, and we got 6 values for wave heights. So we can use HI for each case, right? When you calculate the average value, we call that root mean square we have a definition here. And you can see from the slide. Just use I from 1 to 6 in this case, and you can do the estimation for the average wave height. So just for this case, I think you can have a very quick estimation, and after you have this value, you can have a very straightforward understanding of this wave site. If I was right, I think the average is should be a value like this, 5.83 meters. Am I right? If you calculate the average value in this way, right? So, okay. I take a note here. It's from this calculation. But according to our understanding, if you do the calculation for average value, usually we put them together and divide it by the number of the cases, right? So if in that way, can you do a calculation again? What's the value if we just do the calculation in this simple way? It's about 5.8 meters or, or something. So you can see that the estimations are completely different, but the values, they are quite similar to each other. But actually in waves calculation, we still use this one. Okay, please don't use this one. Okay, it's very quick and simple, but please don't use that. The reason is it's fine in this case because you can see that the values are same. But if we have a singular wave, and I take some points in this way, the results will be different, right? In the simple way, it will be 0. But in the second way, probably you have a value like this, or something like that, right? It will be different. And in your design, of course, you can't use 0, because it means you are doing the design for calm water. That's the reason, okay? So, because we know that we can put all the waves together, all the regular waves together, and we can have a very random water surface in this way. But actually, we can use spectrum to present the feature of the wave combination, right? If you go to the previous lectures, you can see why we can use this function. But anyway, we can use it, and we can have many models for that. You don't have to remember everything, but I want to use the first one to show you an example, and it's a very simple one. We have only one parameter, actually. When you just look at this, it looks like very complicated to use, but actually it's very easy to understand. We need to define a function to present this curve, and by this curve we can present the features of wave, right? No problem. And now if we use the first model, it will be alpha g square omega minus 5 exponential 1.25 omega over another constant omega minus 4. So actually, here is a constant, here is gravity, here is another constant, and you can see that in this expression we have only one parameter, and it's for the horizontal axis, and here the result is for vertical axis. So actually this is a very simple one.
Minus 0.25.
Inside the bracket, negative 1.25. After exp inside,
Yeah?
negative is there.
Negative.
Oh,
Yes.
sorry. Well, anyway, you can see that if we have a proper model, we can use a very simple way to present a combination of singular waves or single waves. And for alpha, in this model, we call that Pearson-Moskowitz model. We need to define alpha, we need to define omega 0, two constants, but actually they are quite simple. The first one, alpha, we define as the constant 0.0081, and omega 0, we call that peak frequency, and we have a definition here. Just for this model, the first one is 0.161 multiplied by g, here's gravity, and over wave height. So, from your observation for open water, if you have a record for wave height, you can define this constant. And the constant alpha, you can just use it as a fixed value, a given value. It means you can define this model, and we can have this function. By this function, we can present the waves like this. So in your design, if you know this model, you know the waves. Okay? So, if you use different reference books or you use your design for different open sea areas, you may have different wave heights, right? In different sea states, in different open sea areas. It means you will have different omega 0, you have different function here, you get different water surfaces. Then you can do your designs based on the estimations here for your waves. Apart from the one parameter model, we also have 2 parameters, 5 parameters, but in our practical design, you should follow your criteria. You may use the first one, you may use the 2 parameter, you may use the 5 parameter. Can we have a break?
Yeah. Yeah. Oh. How about yours? Not mentioned.
Basic mathematics.
Yeah.
You like that?
If I wasn't here,
No.
Time constraint.
So basically, you can know. That's why you
There is even integration calculator. You don't
You have to go and show this calculator to them, and we have to get an approval. I shouldn't show this concept.
show me how you are changing from inches to millimeters.
I understand that.
If this is not there, also we can find out in the calculator. If this is not printed as stick here, also we can find out.
How you can find out if you don't know the numbers? These numbers if you don't know.
Yeah, we can find out in the calculator. It will be short.
Я много мисля, shift conf here. Where have conf here? Where conf?
In calculator, if it's written as fx9 and 1 es, you can store every formula
EF, but I don't have EF.
No, I don't have
Yeah.
You can store, yeah?
You can do integration also. Integration with the
This one.
cheaper one.
因为它在表达一个圆儿啊，每 after 一个2派，它都会有一个周期。你就看这个的话，你每加上一个2派，它都变成一样的。不过我要加点东西，先不搞。
They are not using, they are not using.
I put website. That's the information.
Where you own this? Where you bought it? Amazon. How much is it in Amazon? Here is 9. 10.
That way is 9.
Yeah. That's why it's only. But in what you can do, you can memorize what is common units you are using.
Some of them are
Remember everything, yeah? They are not looking here.
Yeah, yeah.
PSI and BFN one day he used to say he didn't use the metric, he doesn't know anything better. The other one he knows NP after PSI, MAR
They have PSI bar, LBF.
Yeah.
One PSI. Вот это считание. Berbara?
Yeah, Barry.
We have to do this.
BPO handles, so it's
This is the first calculator.
companies, it's all basically wages and annual payment.
So, your one is where?
Varies.
With more the number will be the
Just I
So where it works. No, well, it was also slightly more forward
It was pretty not, it was easy to see, but we didn't realize that
the Jane has
we didn't notice the difference, even though it's big.
India don't have much.
That's why it's only
Sorry? In India, there's no much of unit conversion problem. Mostly they will ask units in megapascal. 1 megapascal is allowed, yeah? 1 megapascal is 1 Newton per minute.
I told him it's a big value.
Rather than writing LBF, yeah? But LBF is not. It's not error, it's correct. But you said last time it's better to change it to megapascal. This is right. This is better.
열고 있어요. 옛날에 2학년 때 어디 있는지 찾고 있어요.
You got to make something.
Yes,
I love
yes.
it.
내가 내
No, we have one more class. 1 hour. Ah, yeah. How about you? Have you brought in? No, one of the.
Today I have things yesterday I had this
You have lessons out there? Yes? But we can join, yeah? You want us? Yes. I'm from building which room? But next week you don't have anything, yeah? Next week you have just 2 subjects. Three. But why not? Ah, but here you have 2, we have 3.
All of us have said.
No. I'm looking why we have 2 subjects today and he has 2 subjects today. But here we have 3, you have 2.
I don't know how much time I MSc project was.
Here's the room.
So that's what it's mentioned.
It's November.
This is also November.
If you're on idea, it's supervising.
31st November.
Alright.
21.
Commercial awareness, you will not get commercial awareness.
Yeah.
No, it depends on some students.
Oh yeah.
How is batch divided?
Okay, guys. Can I start?
Your timetable.
So, no matter which model do we use, but anyway, we can have a presentation like this to give you the features of your waves. If you just look at the meaning of this function or this curve, you can go back to the lecture 2, I think, because we did something for wind. But Actually, they are the same. If we have a massive wave combination and we divide them into different single waves or regular waves, we can have a combination of many waves with the function of cosine something or sine something, right? But anyway, they should have an amplitude for each one. And if you do the projection to frequency domain, you have different amplitude on this surface, right? And if I use this axis for the function over there, and you know that here is frequency, we can connect all the points together, and here is the curve here, right? And from the meaning in this figure, you can see that actually after we know the curve as ohmic, we will know the amplitude of those single waves, right? Or you can have a very straightforward understanding for this combination. But anyway, after you know the height of them, and we know that when we estimate the potential energy of a wave, it should be like something in this way, right? We know density, gravity, and you need the height. After you know this curve, we know the height, or all the heights for all the single waves. It means we can estimate the total energy for the wave from this curve. But please remember that rho and g, or the product of rho and g, is like a constant. And actually from this curve, we know the wave height only. Okay? So sometimes to a wave combination, we call that total energy is the integration of all the things. That's W. Oh, sorry, not W, omega. We call the integration for this curve is the wave energy. But please remember that we also need a constant. It's the product of rho and g. Okay? Don't be confused. After you know the wave energy, we can use this energy to estimate other things, like the significant wave height, it's a very important parameter for a combination of single waves, and usually we use 1/3 wave height. It means if I do an observation for 1,000 waves, and of course they have 1,000 wave heights, right? And I put the wave heights from big to small, I should have a sequence in this way, and here is for wave height. I use the first 333 for calculation. In 1,000, it will be 1/3, right? I just think about this part because I put this sequence as from the greatest value to the smallest value. And if I do the calculation based on this part, it means I have enough safety level. Right? So usually we use 1/3 wave height is from here. Okay? And you can do the estimation from there. It's for 4 times square root of the wave energy, and the wave energy is from here, from the density function. Density function is from here, and this curve is from some models you can select from your criteria. And also, we can do the estimations for average wave height, and it's square to energy, right? All right.
So sorry, how do you derive? Is that theoretically derived that the significant wave height is 4 times the square root of the wave?
It's from estimation, from your empirical observation.
Right.
Yeah. And from here, you can see that to a combination of waves, of course, we always have energy, right? It means the average height is not 0. So again, when you estimate the wave height, you can't just put them together and divide it by your number, right? You need to use the root mean square, right? And of course, you can also estimate the maximum height of this combination and the 1/10, but usually in our design, we use 1/3 height, and we call that significant wave height. The most important thing is here in this slide. Actually, we don't need to understand all the things on this whiteboard because they're really difficult to remember, but we need to know the procedure to estimate the motion of your structures. In the very beginning, according to your observation, we need to define a curve for energy, for your wave energy, and we need to know what is your structure, because for different structures you have different features and you have different scales. We can define some coefficients. That is like a box. You know the waves, and you know your structures, and we can define some coefficients. We should have a good program or coding. But at this stage, you don't need to know how to code your program. But we have waves, we have structures, and we have a good program. Then here is input. Here is black box. And here is output. You can have loadings, you can have motions. So here is the basic procedure for offshore loadings and offshore motions calculation. Okay, and for this part, in our school we have CSAM. It's a numerical software. You can create your modeling for your structures, and they have compiled all the criteria in that software, and you can just select your criteria, give the calculations for loadings and motions. So the procedure is quite simple, but when you do the estimations for the first part, you need to get some reference books for your models. When we talk about the loadings. Please fill this first. You can imagine the feeling on that platform. So you can see that from this video, of course in our design we need to leave really enough margin for that, because you can predict the weather, but you can't control that. And this one is for motion. I have another one, it's for loading. It's in the Indian Ocean, it's for a big ship. It's not for offshore structure. But you can see the wave loads on the ship body. And you can feel the torsion on the ship hull. You may think the ship is strong, this structure is very good, but if you just stand in this ship, you can see the displacement of this structure. It's just like a toy. Can you see the structural displacement? And this video is from, this part is from the engine room, I think. You see? The load is huge. And if you use this ship for many years, of course you have fatigue issues. Can I carry on? So when we estimate the load or the motion, we have two different methods. The first one is very simple. We call that Morrison equation. I think you have heard that before. And the second one, we can use potential theory to do the same estimation. Today, in this lecture, we focus on the first one, Morrison equation, and it's just about the expression. It's quite simple. The force is from some factors like the density or constant, the volume, I got this from Professor Longbin, but I think he made a mistake in this expression. It's much better, right? Sorry?
I was just wondering, could you, perhaps we'll cover it, but could you just describe up to what wave height should you integrate when you use this to determine total force? So obviously wave run-up can be quite a significant factor.
In Morrison equation, we don't have wave height.
But when you integrate, you're going to get a total force, you're going to need to integrate that over the height of the column.
The integration is for this pillar. It's for the pillar height. And the df is for a part of this pillar. It's not for wave height.
But to calculate total force, you need to integrate over the height of the pillar.
Yes,
So
but
what
it's
height-
for pillar. We don't have any height for the waves in this case when you use Morrison equation.
Okay.
You can come to me after this lecture, okay?
Yeah, that would probably be
So if we just talk about the force, I prefer this expression in my note. But in Professor Longbin's material, when you see the expression in this way, it's just for a small element on this pillar, okay? And here is the displacement of this pillar. We assume that if your structure is this pillar, okay? And here is pi d squared over 4 multiplied by the height of the pillar, right? So if you go back to that expression in Professor Longbin's material, you can see that it's just for a small element. And we don't have this h, right? That's why you can see pi d squared over 4. Because we need it here for the estimation of the displacement if here is water surface. Okay. And in Morrison equation, we have two parts. The first part, we call that initial part. And the second part is for drag force. In this equation, U is for the velocity of water particles, or the velocity of that wave impacting on this structure in this way, in the normal way. Okay? So I think you are familiar with this part. When we estimate the drag force on something, you need the surface area, you need the density, you need the constant, and you need the velocity square, right? And we use this way to get the direction. Okay? So, to any structures, after you have the modeling, we can estimate the constants, and then we can apply the Morrison equation to estimate the force from wave. Okay? It's not based on any theories. It's just for estimation, and it works very well. When we apply Morrison equation, we have two parameters to define. The first one is Kc, and we call that Coulomb-Carpenter parameter. It's a dimensionless ratio. Of the two parts. The initial force over the drag force, or the initial effects over the drag effects. And for the dimensionless definition, we use the wave velocity or the water velocity on the structure, the wave period over the characteristic length of your structure. When we present the frequency of waves, we use small f, right? But in a dimensionless form, we can define another parameter. Here is viscosity, here is the characteristic length of your structure, and here is the real frequency. By this way, by this ratio, we don't have any unit, and we can use the dimensionless form to present the wave frequency. So when we use Morrison equation, sometimes you can see the two parameters like this, and in your application, you may have some plottings to decide your Cm with Kc, or Cm with frequency, or CD in the same way. You may have many plottings from different reference books, but when you use the plottings, you need to know the Kc first, and here is the Kc, okay? After you know the wave, of course you know the wave velocity and the wave period, and after you know the structure, you know the length or according to different definitions, you may have different characteristic lengths. But anyway, it's from your structure. So you can calculate Kc or estimate Kc. From reference books, you can find out how to give the values of Cm and Cd, and then according to the equation here, you can estimate the forces or loadings from waves. Okay. So in fluid mechanics, we have another very, very important constant. Oh, sorry, it's not constant. It's a parameter. We call that Reynolds number. And we use Reynolds number to decide the flow is laminar or turbulence. If it's smaller than 2000, roughly 2300, we assume that the flow is calm, and the flow layers will be very good, and we don't use any turbulence models. But if it's greater than 2300, we need to include a turbulence model in your simulation. So according to the definition of Reynolds number, it should be velocity over a length, velocity multiplied by a length and over viscosity of your fluid. So if you put them together, you can see that Reynolds number will be the product of Kc and alpha. Okay? When we use Morrison equation in this expression, U dot and U, they are for the waves, and we assume that the structure is just standing here. It has no motion. But sometimes this structure is moving around, right? Like in the first video, you can see that. And in that case, when we estimate the wave force by Morrison equation, we need another term. It's the first one. M is the mass for the structure, and x dot dot is from the structure motion. It's acceleration of that structure, okay? Because the first dot is for velocity, the second order is for motion. The second order is for acceleration. But anyway, in this form, we include the motion of structure already. If you can use some methods to estimate the motion here, again, we can use Morrison equation to estimate the load on that. Okay, in these slides, we can see two plottings. If you look at them carefully, you can see that if we can estimate Kc, we can estimate Cd and Cm. It's wrong. It's in this slide it's Ca, but actually it's Cm. Okay. So if you can estimate the ratio here, you can have Cm and Cd, and you can estimate the load from waves. In this picture, I can show you a laboratory facility for the test, and you can do the validations for Morrison equation. They use a pump in this area to generate the waves, and in this horizontal tank, they can have wave. And if you put the your structure here, you can test or you can measure the wave from the you can measure the loads from the wave. And then if you have if you have a projection constant, you can estimate the real case or real load in practical case. Okay. About Morrison equation, another point is, if we look at your structure, we assume that it's a pillar. From top, we can see the cross-section areas like this, and your wave is from this way. By Morrison equation, you can only estimate the force in this way. Okay? And we call that inland force or normal force. But actually, if I show you a video on this pillar, we should have another force. And then the pillar will have a motion like that, right? It happens to riser, to pipeline, and to a huge pillar. So actually, when you have wave, you have water particles in this way. They will hit on the structures. In the meantime, together with this force, we have a transverse force. And we have some methods to estimate that. But please remember that for the force in this direction, it's quite related to the wave features. If you have a function to present your wave, you can just estimate this force, and please forget the bottom one, just look at this one. It's the frequency or the force of just the force. The force in this way. And the first two, they are the wave velocity. And the third one is the wave height, if you do an observation. So you can see that they are quite similar to each other, right? So after you have this function, you can just estimate this force. But for the transverse force in waves, it's quite different with all the others. And for this one, usually we use computer to do the estimation for the transverse motion. Because from this video, if you look at again, it's not only about the force on that, it's also about the vortex shedding. So we have too many factors to think about. You can see the shedding just behind that, right? The last one thing about Morrison equation is the current, and we can include this factor. If the current velocity is not very big, In the original motion equation, we just think about wave, and if we use u0 for your wave velocity, but when we think about the current velocity, we can use capital U, and in this case, we put them together for the drag force. Okay. And we keep the first term the same. We don't change that. But when we include this factor, we have some criteria. The first one is small r, the ratio of your current force in this combination. And you can have a table to check the ratio. Then we can have a correction coefficient to make a correction for your estimation according to motion equation. And in this slide, you can see how to estimate the parameter here. Okay, and you can always find some tables like here from different criteria. So if we want to include the factor from current, we have new velocity, we have new constant, and here is about how to get the new constant. Okay. The last one thing today, when you do the correction for the current, you can calculate the value of R, but when you check the tables from different societies, you can always see that it's only to 0.4 or sometimes to 0.3. That means from this expression, you can see that if the value of R is very big, it means the part of current is very big, right? So if this part is small, we can use the correction here. But if this current is very big, it means we can't do the correction anymore. We can only use Morrison equation for wave only, and we use another method or something like the current or something U square or similar thing like this, to do a separate calculation and put them together. Okay. So I think I can finish here today, and in next 2 lectures we will focus on the dynamic motions of your structure. Okay. In the end of this material, you can see some plottings, but I don't think they are very important, because from different criteria, you can have different plottings. But as long as you have the calculation for Kc, you can estimate the constants, and then you can use Morrison equations to estimate the load. Okay? And after this lecture, I will upload this material to your Blackboard. You can download if you want to have a look again. But I think before that, I need to change something in this material, because I just found that something is wrong.
Professor, is the Morrison equation applicable all the time?
Over what?
applicable. As far as I remember, there is an important condition that d over lambda is smaller than 0.2.
Yeah, we do have a criteria.
So,
We do have a criteria. Yeah, it's for small waves and small structures.
I can't get it.
and if that is a small structure, what should I resolve about to calculate a number?
About just adding one. Where do we use this one? So what kind of function? I mean, what kind of wave? Was this one we use for the force here? Yeah. So, but you said this applied one. When do we?
In the lecture 2, we have a similar calculation for wind, right? We say that is static pressure. We can use just in that way. And if the immersion equation is for waves only, we use this one to estimate the current force and wind, because they are quite similar.
Together.
Not together, from wind and from current.
Okay.
Yeah, but you use different constants. The format is quite similar.
For the wave flow,
Yeah,
and just have this one. If you have
this one, because you may have different calculations according to different criteria. I can't promise you must use this one.
No, what I'm saying, so it's quite, difficult to understand where do we use this one. What kind of criteria you
Or in that way, you just get this one. Because in our estimations, it's as far as I know, in most estimations, it's always smaller than 0.4. So actually, you don't need to think about this one, unless you have some special requirements to say that you can't use this one. Because if you can use this one, it always covers your cases.
So if it's, for example, less than 0.4,
Yeah.
or more than 0.4.
Yeah.
So what we use? We use this one, if it's less than.
Yes.
If we say 0.3, or what?
When you calculate R,
Yeah.
in most cases, it can be covered by this table. So please get this one.
Yeah.
Yeah.
My question was related to if you can I borrow a pen?
Yeah, of course.
If you have a column like this and you have a wave impacting it, then in order to calculate the total force on the column, you need to integrate.
In this case,
I actually did a project at my undergrad considering the effect of this, because you can either integrate from the still water level